So, dear students, in this video, I'll proceed the video that I have already uploaded regarding feedback of amplifiers, and we understand that there are two types of feedbacks that we can adapt for an for an amplifier, sorry, so that we can enhance the sensitivity of the amplifier, and we can enhance its stability. So here in this video, I'll be proceeding from the previous video that I already talked about. So in our previous video, I have obtained a result for the gain a dash as 1 by 1 plus beta A. This was the result that we obtained in our previous video, and this is the gain in presence of feedback, and probably the feedback in this case is negative. We rightly remember, for positive feedback in the denominator we obtain a negative sign, and in case of negative feedback we obtain the positive sign. So in order to proceed from here, what am I supposed to do is that I want to take negative feedback. I want to take negative feedback in consideration, and since negative feedback has it has a range of properties, that it becomes very plausible to make use of negative feedback, because by making use of negative feedback we are able to stabilize the working of an amplifier. We are able to stabilize the gain of the amplifier, and we are also able to stabilize the sensitivity of the amplifier using negative feedback. So here we'll be analyzing, first of all, we'll be analyzing uh, the stability in current gain. So this should be the stability of current gain. So in order to achieve some mathematical stability for this statement that I have written here, I will start with this equation. So if I write the gain for an amplifier in where we are subjecting the amplifier with a negative feedback. So when we do that, we can make an approximation here, an approximation like that the feedback circuit uh, that we make use in case of negative feedback, we'll design it in such a way that this beta A is very greater than that of 1. So if we are able to achieve this condition, we can make use of this approximation in this equation, and once we do that, we'll get A dash is 1 by beta A, because beta A is very greater than that of sorry, I have committed a mistake here. Here it is A. Okay, here it is A. What is A? A is the gain of the amplifier in absence of the feedback that we are applying, and A dash is the gain of the amplifier in presence of feedback. So once we achieve this thing, uh, we can understand from this equation that the gain of the amplifier is independent. It is independent of A. So it simply depends on beta. And what is beta? So A dash is 1 by beta. So what is beta? Beta is the feedback ratio, and we can see that there is automatically stability in the current gain of the amplifier when we are making use of negative feedback. So, in this case, we will be discussing the decrease in amplifier sensitivity, and this I have already talked about the negative feedback, because negative feedback has advantages over positive feedback. So here is another important parameter. We want to see what's the outcome of this parameter, and that is sensitivity. Sensitivity of amplifier. So when we make use of negative feedback in an amplifier, we'll see that this overall sensitivity of the amplifier will decrease. So to start with, the right thing here is to define this sensitivity. Let us assume that this sensitivity is S, and this sensitivity is defined as the fractional change, the fractional change in the gain of an amplifier in presence of feedback. So that gain is a dash divide by fractional change in A. And we understand that this A is the gain of an amplifier in absence of the feedback, and A dash is the gain of the amplifier in presence of negative feedback. So we can write down this in a mathematical way, something like delta A by delta A dash by A divide by delta A and A. So we have the ratio between fractional change in A dash and the ratio between A. So this overall ratio between the fractional change in A dash and fractional change in A is defined as the sensitivity of this amplifier. Now, to make it simple, I can go with dA dash by A dash divide by dA by A. So from here, I can move from here. This is dA dash by A dash. This is A by dA. So I can say that this sensitivity is it is A by A dash dA dash by dA. So here we can see that we are supposed to differentiate A dash with respect to A, right? So let us go back to A dash and what is A dash for negative feedback in an amplifier? That A dash is it is A divide by 1 plus beta A. So if I have to proceed from the previous equation, this sensitivity will be A by A dash d by dA of A dash. So what is A dash? A dash is A by 1 plus beta A. So we can make use of u by v rule here. If we have d by dx of something like this, we have, sorry, it is u by v here in this case. So v as its into differentiation of u minus u as its into differentiation of v whole divide by v square. So we'll make use of this formula here. So so what will be s? S will be a by a dash, and here in the denominator I will have 1 plus beta a whole square. So here I'll have v as its, that means 1 plus beta a as its, multiplied by differentiation of u. So a differentiation of a with respect to a will be 1. Then minus u as its, so a as its into differentiation of 1 plus beta. So differentiation of 1 will be 0 and differentiation of beta a will be beta. Right? So I see this beta a and beta a is cancelled. So s will be a by a dash times 1 by 1 plus beta a whole square. Right? So let's move on from here. Now, so sensitivity comes out to be a by a dash is known to us, that is a divided by 1 plus beta. Okay, so here we have 1 plus beta whole square. So s will be, this a and a will cancel, this 1 plus beta will go up, so this is 1 plus beta a beta a beta a, okay, whole square. This square and this term will cancel, so we are left with the sensitivity equal to 1 by beta plus a. So we can see here that that what's happened to the overall sensitivity of this amplifier when we have used the negative feedback. If you rightly remember, what is a negative feedback is that a part of the output of an amplifier is given back to the to the input of the amplifier in such a way that the output of the feedback circuit that used to be there, if I go back to that situation, it was like this. We had an amplifier, we had the terminals for this, and we had a feedback circuit, and from here we we had the output, and this was feedback circuit, and here we used to obtain the output from the feedback. So if this signal was having a phase like this, uh, through amplifier, its amplitude goes up, and we make use of common base amplifier here. And then we subject this output back to the feedback circuit. And what feedback circuit does here is it changes the polarity of the signal, the output signal here, and it changes the polarity by 180 degree. So in that case, I will have I will have an output of nature like this. So so this is going to oppose the signal that we have introduced to the amplifier. So this is what is called as negative feedback. So in case of negative feedback, we can see that this sensitivity is the reciprocal of this parameter. So so it's clear from this equation that there's a sharp decrease in sensitivity of the amplifier. So if I compile the two things that we discussed, the first thing we discussed was the gain, stability in gain, and gain stability using negative feedback. The second important thing is sensitivity, and here we have seen that the gain is independent of everything. It only depends on the feedback ratio beta. So here we are sure about one thing. What is that? That is that if there is variation in the frequency of the system, or if there is variation in the temperature, the gain of the amplifier will not be disturbed. It will not be disturbed because the gain is independent of the temperature. It's independent of the frequency that might be changing in the system. And the next important thing was sensitivity. And in case of sensitivity, we have seen that the sensitivity of this amplifier decreases because it comes out to be equal to the reciprocal of some good number. So this is another important application of negative feedback that we make use in amplifiers, and certainly making use of negative feedback gives these two important applications. One is stability in current gain, and another is decrease in sensitivity of the amplifier. So now let's talk about another application of the negative feedback that we have discussed. Uh, this application is a reduction in distortion. So what does it mean, first of all? I mean, yeah, if we talk about an amplifier, we can have a signal which has large amplitude, and this signal can have uh, distortion in it. It can have some harmonics in it which are not favorable. So, uh, how can we, what will be the impact of making use of negative feedback if we want to see the reduction in this distortion? So, That means the output that here we will obtain, it will have distortion with it, because the distortion is already present in the input signal. In addition to the signal itself, the distortion will also be amplified. So if we go back to the system, we have an amplifier, and we subject some input uh, to this amplifier, and we have an output. So there will be the distortion associated with the output in absence of feedback. So what I'll say here, what I'll assume here, I'll assume that D is distortion. This is distortion in absence of negative feedback. Right? So the moment I'll make use of a feedback circuit, say I'll put it here like this. We have a feedback circuit here, and we have an output here, and this output will be subjected back to the input signal of this amplifier. So let me assume that the feedback circuit has a feedback ratio as beta, and is the gain of the amplifier. So here, this is my amplifier, and this is my feedback circuit. So let me assume that that if I start with the distortion D dash. Okay, now so here this D dash will be input to the feedback circuit, and here I'll get some output. That output will certainly be BD dash. I mean beta D dash. Now this beta D dash, we have to keep in mind that we are talking about the negative feedback. This beta D dash will be input to the amplifier. So what's going to happen here is that this beta D dash will be amplified, and the thing that will obtain here will be a beta D dash. So the things will look like this. You will have beta D dash as input to the amplifier, and you will have a beta D dash as output from the amplifier. Now, in order to proceed from here, what should I go with? I should go with the symbols that I have used. So D is my distortion. Distortion. Can call them harmonic distortions, and that too in absence of feedback, right? And then we have D dash in presence of feedback. So if I go back to the previous thing, I can write here feedback distortion, and we had obtained it as beta D dash, and then we have amplified distortion, and this we have obtained as a beta D dash. I mean, you can see it, what we have already discussed. So, so this will be my, this beta d dash is the feedback distortion, and this a beta d dash will be the amplified distortion that we will get at the output of the amplifier. So, so I would like to write the net distortion. So what will be the net distortion? That net distortion I will write as d dash. This net distortion will be d minus a beta d dash. Now, we understand that this D is the distortion in the amplified signal in absence of feedback, and D dash is the distortion that we will achieve once we have subjected the system to the negative feedback. So this negative sign it's quite obvious here that this negative sign is coming because we are making use of negative feedback. That means the output of the feedback signal is out of phase with the input signal. So once the two signals will superimpose, the resultant of the two distortions should give us the less magnitude. So if I manipulate this equation, it will be like d dash plus a beta d dash is equal to d. So here I can have d dash out. This is 1 plus a beta equals d. So finally I'll get d dash equals d by 1 plus a beta. So see, the result is very convincing, and the result is very applicable. And what this result says, it simply says that the distortion that we achieve once we have used the negative feedback to the amplifier, the distortion that we will achieve will be less than that of the distortion that we have in absence of negative feedback. So here we can understand that the overall distortion, the unwanted harmonics that are present inside this that are associated with the signal, their component, the magnitude of their component can be decreased by making use of negative feedback. Negative feedback in the circuit, in the amplifier. So with this, we would like to stop because I think it's clear to us what happens to the distortion when we make use of negative feedback to the amplifier.